Welcome to AI Frontiers. This episode examines a pivotal moment in machine learning research, captured through 68 papers from December 27, 2025. This snapshot reveals a profound shift in the field's priorities, moving from a singular focus on raw capability toward a deeper quest for reliability, efficiency, and trust. Today's journey will uncover four dominant themes driving modern AI research. We will explore three groundbreaking papers with transformative potential and understand the key methodologies powering today's breakthroughs. The presentation will also look ahead to future research directions and challenges, illustrating how AI is maturing from being merely brilliant to becoming truly trustworthy. The state of machine learning is one of transition. While deep learning has achieved remarkable capabilities, it now faces significant real-world pressures as models move from academic benchmarks into critical domains like hospitals, power grids, and climate science. A model that is 99% accurate on average can still fail catastrophically on rare cases. Current research is shifting from pure scale to a rigorous scrutiny of foundational principles. This snapshot captures the field maturing into a tool of dependable operation. The first major theme is robustness and reliability, which can be described as engineering the conscience of AI. This is exemplified by work from Thompson and colleagues who established theoretical bands for uniform reliability in medical AI, ensuring models do not fail silently on rare conditions. Other research includes automatic debugging frameworks for massive cloud service logs and fixes for hidden instabilities in large language model fine-tuning. The collective goal is to move beyond average accuracy toward guaranteed performance. View 2 is efficiency and scalability, focused on breaking down computational walls. A key innovation is phase gradient flow, which enables constant memory analysis of genome-length sequences. Other advances include methods for training massive mixture of experts models across federated networks and dynamic mixed precision training that saves computational cycles. This work makes powerful models practical for real-world deployment by overcoming memory, communication, and energy constraints. The third theme is advanced optimization, which involves rethinking the learning factory itself. Research includes designing smart curricula based on data variability over time and blending imitation and reinforcement learning to create more generalist agents. The use of alpha divergences is creating more stable objectives for learning human preferences. This theme is about mastering the art of sculpting neural networks with greater precision and reducing wasted effort in model training and fine-tuning. The fourth dominant theme is interpretability and mechanistic analysis, dedicated to opening the black box. A landmark finding is a mechanistic explanation for federated learning failure, identifying the collapse of specific sparse circuits within models. Other work directly measures the computational effort in a model's reasoning process and builds interpretable sleep staging models tied to clinically meaningful patterns. The field is moving from mystery to mechanism, building glass boxes instead of black boxes to enable scientific trust. Several key findings from the day's research represent genuine leaps forward. These include long-range distillation, where AI-generated synthetic data overcomes fundamental climate data scarcity. Phase gradient flow enables genome scale sensitivity analysis on single GPUs. A paper titled Fusion or Confusion found that complex multimodal fusion architectures often fail to beat simple baselines. Another provided a mechanistic explanation for federated learning failure via sparse circuit collapse. These findings challenge core assumptions and open new research directions. Common methodologies powering this modern research include surrogate loss functions with H-consistency bounds, which provide theoretical guarantees for optimizing complex objectives. Parameter-efficient fine-tuning, notably low-rank adaptation or LoRa, adds specialized overlays to frozen foundation models. Sparsity-inducing regularization creates smaller, faster, and more interpretable models. Advanced federated learning frameworks are designed to handle statistical skew across decentralized data. These tools enable more precise, efficient, and trustworthy AI development. The first selected deep dive is into the work by Thompson and colleagues, titled Uniform Convergence Bounds for Generative and Vision Language Models. This paper addresses a silent crisis where models are reliable on average but can fail catastrophically on rare, unseen cases. Its key insight is that uniform reliability depends on the low-dimensional structure of semantic manifolds, not the total parameter count. It provides a mathematical framework for determining sufficient training data, enabling regulators and practitioners to ask if a dataset is adequate to prevent catastrophic failures in high-stakes domains like medicine. The second paper is by Lee and colleagues, Taming the Tail, Stable LLM Reinforcement Learning via Dynamic Vocabulary Pruning. This work solves mysterious training collapses during language model alignment. It identifies a hardware-rooted villain, a precision mismatch between high-precision training and lower-precision inference. This mismatch makes low-probability tokens in the vocabulary tail create systematically biased and noisy learning signals. The solution dynamically prunes this extreme vocabulary tail from the reinforcement learning objective, trading a small known bias for the elimination of large destructive variants. This enables more predictable and robust development of AI assistants. The third paper is by Martin and colleagues, Long-Range Distillation, Distilling 10,000 Years of Simulated Climate. This work shatters a fundamental dilemma in AI weather forecasting. The methodology uses a high-fidelity, short-step AI teacher model as a data factory, generating a synthetic climate dataset spanning 10 millennia to capture slow planetary oscillations. A long-step student model is then trained entirely on this synthetic data. The result is a student model whose forecast skill rivals the world's most expensive numerical supercomputer models. This represents a paradigm shift, proving AI-generated data can overcome fundamental scientific data scarcity. Future research directions illuminated by this work point toward foundation models with built-in knowledge from domains like physics, biology, and logic. There is a push for unified theoretical frameworks to provide a more rigorous backbone for the field. Decentralized and heterogeneous learning will advance to handle complex multitask ecosystems. AI-generated synthetic data is poised to become a major pillar for scientific discovery. The integration of data-driven learning with domain-specific constraints and guarantees will be a central focus. This presentation was created through a synthesis of the 68 research papers using a large language model. The narration was generated via text-to-speech synthesis, and visual concepts were informed by image generation models. A human expert reviewed the content for accuracy and narrative coherence. It is important to note that while reviewed, some oversights may exist. All references to the original papers are provided for further exploration. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the arXiv preprint server.